Now that you've seen how the ideal gas law can be used to relate different variables that define the state of a gas, we'll talk a little bit further about how you can use the ideal gas law to do some calculations. I've mentioned before that one of the really powerful things about the ideal gas law is that it defines the state of a gas, and if you know any three of these variables, P, V, N, or T, you can use the ideal gas law to find the fourth variable. But there are a couple of important things that you need to be aware of before we start doing calculations. The first one pertains to temperature. There is a limit on how much you can cool something. The limit is a temperature called absolute zero, which is negative 273.15 degrees Celsius. This is the lowest possible temperature that you can make anything. We're going to use this knowledge that there is a minimum possible temperature to define a new temperature scale called the Kelvin scale. This is an absolute temperature scale that sets the minimum temperature of negative 273.15 degrees Celsius to be equal to 0 on the Kelvin scale. And to convert between Celsius and Kelvin, what you can do is say that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. This conversion will be given to you so you don't have to memorize it. But one thing that's really important to be aware of when it comes to the Kelvin scale and the ideal gas law is that you must always use temperature in Kelvin when you use the equation PV equals nRT. And we can get some idea as to why that might be the case, right? Like, for instance, if you were talking about a process that was occurring at the freezing point of water, which is 0 degrees Celsius, if you were to plug 0 in as the temperature here, that's going to cause all kinds of problems with the equation PV equals nRT. It would make you think that at 0 degrees Celsius, right, at the freezing point of water, there is a pressure of 0 for gases. And we know that gases exert pressure at 0 degrees Celsius. So, this is why you cannot just use temperature in Celsius, because you'll get answers that don't make sense. You've got to make sure that you're always using temperature on the Kelvin scale when you do PV equals nRT. We can also talk in more detail about the gas constant, which is R. So I mentioned previously that that was just a constant that was in the equation PV equals nRT. It's a proportionality constant. And you'll see a few different values of R. The value of R that you use depends on the units that the value takes. The most common values of R that you'll see are this. There's the small value of R, 0.08206, which has units of liters times atmospheres divided by moles in Kelvin. Or there's another value of R that I sometimes call the big value of R, which is 8.314, and the units that this value carries is joules per mole per Kelvin, right? So these values are the same. The only difference between them are the units. Now, one more thing to mention regarding the big value of R and the units of it, joules per mole per Kelvin. A joule is a unit of energy, and that's going to be really important for us to consider as we continue on in the chapter and we talk about how we can calculate average kinetic energies of gases or molecular speeds or other properties such as that. The value of R expressed in liters atmospheres per mole per Kelvin will tell us information about the volume or the pressure of the gas. Now, how do you know which value to use in problems? What guides you should always be the units. Always take a careful look at the units that you're given in the problem. If you have a problem where you're given a volume in liters and you have to calculate a pressure in atmospheres, then you're going to want to use the small r. If you have a problem where you're asked to calculate the kinetic energy of a gas in joules, then you'll want to use the big value of R, 8.314. So look very carefully at the units to give you a guide on which R you're going to use to solve the problem. We can also define something called the standard temperature and pressure of a gas. We define that the standard temperature is 0 degrees Celsius and the standard pressure is 1 atm. And you'll often see this abbreviated as just being STP because we so often deal with gases under these conditions that it can become very cumbersome to always write 0 degrees Celsius and 1 atm. So we'll just write what's going on with our gas at STP. Let's take a look at an example problem. This example problem asks us to calculate the volume in liters of 1 mole of an ideal gas at STP. So we don't have to write out at 0 degrees Celsius and 1 atm. Let's talk about how we're going to use the ideal gas law to get the answer to this problem. So the ideal gas law says PV equals nRT. And as I've mentioned before, if you know 3 of the 4 variables here, then you can find the 4th. We know the number of moles of gas because you're told you have 1 mole. We also know the pressure is 1 atm, and the temperature is 0 degrees Celsius. So we know 3 of the 4 variables. We're missing the volume, but we can use this equation to help us find it. What I can do is solve the equation for V, and that will be done by dividing both sides by P. So V is equal to nRT over P. And now I can plug in the numbers. So we're told that we have 1 mole of a gas, and we recognize here that we're asked to calculate the volume in liters, and so we want to use the R that contains units with liters. We want to use 0.08206. So 0.08206, and the units are L atm over mole K. Always write the units so that you can see how it cancels. Temperature. Remember that whenever you use the ideal gas law, you must use temperature in Kelvin. Because if you were to plug in our temperature of 0 degrees C into this equation, right, anything times 0 is 0, so that would make you think that the volume of a gas is 0 liters at 0 degrees Celsius, right? But we know that at STP, gases occupy volume, right? We know that at 0 C, gases will occupy some volume, so you cannot just plug in 0. You've got to make sure that you convert this to Kelvin by adding 273. So plus 273 gives you that the standard temperature is 273 Kelvin. That's the value that I'm going to put in for temperature. Divide by the pressure, which is 1 atm. And now we can go through the units. So we have moles divided by moles. We have Kelvin divided by Kelvin. And we have an atmospheres divided by an atmospheres. All that's left is units of liters, which is a good thing because what we're finding here is a volume. And the volume that you'll get comes out to 22.4 liters. That will be the volume occupied by 1 mole of an ideal gas at standard temperature and pressure. That brings us to the end of this video. In our next video, we'll talk about changes of state for gases.